Hi, my name is Caitlyn Obrero. I am a student at NC State, and today I will be talking about photon number resolving with a temporally multiplex loop. So if you know a little bit about the camera in your phone, you'll know that there is a little detector that can sense light, and it does this by absorbing it and then turning it into an electrical signal. Well, we also know that light is both a wave and a particle, and this particle is a photon. And because of the development of single photon sources, fiber optics, and single photon detectors, we're now able to be able to look at these individual photons. And the ingenuity of using these photons really comes from the fiber optics, which allow information encoded into the photon to be traveled very long distances with relatively little loss. However, the issue with these systems is that the detector can't determine whether it's one photon or multiple. And so a lot of systems that is being researched now often operate at low power regimes where the probability of a photon or multiple of them being generated at the same time is relatively low. But also the probability of a photon being generated at all is also very low. And if we want more information, we want more photons, so we want more power. And so there are several ways that people have gone about this. Two ways that this physical review paper have mentioned is a spatial array and a temporal array. And so the spatial array is where the photons are separated into multiple detectors, while the temporal array is where the photons hit one detector, but it's separated over time. And so I looked at the temporal array. And so here's the system that I devised and built. If you want more information about this, feel free to come to me at the poster. But I'll go through this really quickly. So the fiber loop is made by a 2x2 fiber coupler that is spliced together with extra fiber to account for a delay. And so within the loop itself, the light is being reflected and transmitted. And what determines what is stays in the loop and what comes out of it is the entry point into the coupler and the coupler ratio. And so we can determine the probability of a photon coming out at a particular time then using this function above. And so this is what it looks like when we have different coupler ratios. So we have 0.1, 0.3, and 0.5, and you see that they're all varying probability distributions. And so for us, we use a 0.3 or a 3070 coupler, and then we also use 24 meters of fiber for the loop. We also devised a way to carve pulses so that we can use other light sources such as like ASC, so that we can use different photon statistics. We also have to attenuate it down to the single photon level. So here we have a 99.1 coupler, which is 20 dB, another 20 dB, and then a variable attenuator. And then we split this off 50-50, one going to our loop, the other going straight to our detector to serve as our control. And so we first started off classically with a 1 megahertz pulse, and you can see that within this microsecond of time that we can see about 6 peaks, and these peaks are separated by 128.7 nanoseconds. And this is characteristic of our loop because of the fiber slate. And so quantum measurements are a little bit different. We do this via time tag. Time tag is where we have a pulse, and then we have the arrival time of a click that comes from it. And so you can kind of see here as an example that with this added time factor from the loop, that we get more information on a pulse by pulse basis than without it. And so we get this result of clicks or no clicks that we can take for millions of photons or millions of pulses at the same like simultaneously. And so this is what it looks like when we have a million pulses, and we can see where the clicks end up within this microsecond time frame. And so it looks very similar to the oscilloscope trace that I showed before, but one thing to note is that this is for 67 dB of attenuation, or negative 90 dBm, or 1 nanowatt, which is really small. That's less than 1 photon per pulse, and we want to go to higher power regimes. So this is what it looks like when we decrease the attenuation, so we're simultaneously increasing the power, and you can kind of see here that the second pulse kind of reaches a saturation point at 1 million counts, followed by the rest of them. And so that implies that at some power level or attenuation level, the probability of a pulse with a lot of photons clicking each bin increases. One thing to note is also the number of bins that we have, which I'll talk about in a bit. So we can also determine the average click count, which increases as power increases. But one thing to note is that the number of clicks that we can resolve, it cannot be greater than the number of bins that we can observe. And so I mentioned before the bins, and we can only see about 7. So we can only see 7 clicks. However, another thing to note is that the photon number is not always the same as the click number. And so how do we know when we've crossed that threshold? And so we can reference our control data. So the click probability versus attenuation can help us clue into what the probability, photon probability would be at past saturation. And so the click probability versus attenuation at low power are linearly proportionate to one another. And we can extrapolate that past saturation to say, oh, at 60 dB, we may only see one click per pulse, but from this extrapolation, we can estimate, oh, it could be 1.5. And so we also compare this to a carved pulse. We have this very similar trend here, but one thing to note is that there's existence of a background, which we can't just cut out because we don't know if these clicks are coming from the pulse or from the background. And this is also an issue for our detector because our detector tends to get overwhelmed when we have a lot of counts. And so we can't go to higher power regimes like we want to. However, we can still use the information that we do have, at least the linear part, to extrapolate past saturation to see what the photon probability would be if we had that information. And so in conclusion, we have developed a way to temporally resolve multi-photon events, both on a pulse-by-pulse basis and an overall distribution basis. And we hope that as we continue to refine our system, that we can use it for higher power regimes and for different light sources to see the difference between the two. So yeah, I would like to thank Dr. Murphy for advising me, Michael Gill and Evan Dowling for their help at LTS, everyone at Trent and Daniel Serrano. Thank you.